After studying this module, students, you should be able to understand the meaning of the mathematical expectation, the concept and types of a random variable. You should be able to distinguish between discrete random variables and continuous random variables, the concept of probability distribution, the computation of the mathematical expectation, which means the expected value of a discrete probability distribution, the variance and standard deviation of a discrete probability distribution. So let me introduce the subject to you. The ultimate objective of this module is to help us to compute the expected outcome or value, variance and standard deviation of the experiment by examining the concepts of random variable and probability distributions, thereby enabling us to select the best decision among a number of alternatives in business and managerial decisions. Decision making with or without sample data is always with some degree of uncertainty. The central function of statistics is to develop principles and methods that will help us make decisions in the face of uncertainty. Our need to cope with uncertainty leads us to study and use of probability theory. Probability is a way to quantify uncertainty and provides a foundation for the scientific analysis of problems involving uncertainty. Its application enables us to obtain a degree of predictability from uncertain states of nature. Thus, before learning statistical decision procedures, we must acquire an understanding of probability theory. In our earlier module, we have discussed the various ways of assigning probability values to the outcomes of an experiment. In this module, we discussed the application of the probability theory to real life situations when the decisions are based on expectations about the value of a variable like the life of an electric bulb, a car battery, sales of a firm, demand of a product like a refrigerator or your mobiles. So we can have different examples from our day-to-day life which are our real world situations. So in application of probability to practical situations, interest usually centers not on the detailed outcome of a random experiment, but rather on the numerical characteristics associated with these outcomes. The characteristics are measured with the help of one or more variables. The values of the variables, as the name suggests, vary from individual to individual, time to time, item to item, or from unit to unit. The variations in the values of a variable usually show systematic patterns in the variation. What are these patterns? These patterns are called distributions, indicating distribution of values of variables. Now, in this module, what we are trying to discuss and learn is extend the concept of probability to explain the probability distributions. In a layman's term, a probability distribution is a numerical or a graphical depiction of frequency counts or probabilities for various values of a variable that can occur. So let's understand what is a probability distribution. A probability distribution provides a complete description of a random variable or the population over which the random variable is defined. However, it is often necessary to characterize the distribution by a few summary measures, which means we want to summarize that information. So we have already dealt with the question of how a sample of data may be arranged into a frequency distribution and summarized by measures such as arithmetic mean and standard deviation, or the square of it, the variance. The corresponding population measures are the mean or expected value of a random variable and its variance. So just as we calculate mean of sample data, we can also determine the mean of a probability distribution. The mean of probability distribution is called the expected value or EX and is found by multiplying each value of a random variable by its probability and summing the results. Or in other words, this is sigma pi xi in terms of a formula. The various characteristics of the expected or theoretical probability distribution of a random variable x are: first, the mean denoted as Ex, the variance and the standard deviation. The probability distributions deal with expectations. They provide useful models in making inferences and decisions in the face of uncertainty. The computations of expected value, variance and standard deviation, as discussed in this module, of the probability distributions can help select the best decision among a number of alternatives.
Mathematical expectation or the expected value of a discrete probability distribution. In general, mathematical expectation can be interpreted as the average value obtained in a long sequence of repeated experiments. If an experiment is repeated a very long number of times, we would expect the relative frequency distribution to approach the probability distribution of the random variable x. In the limit, this relative frequency distribution and the theoretical probability distribution would be same. In general, we may interpret probability distributions as the theoretical frequency distributions based on very many repeated observations of the same experiment. Thus, expected value may also be interpreted as the mean of a discrete random variable. It represents the arithmetic mean of a theoretical probability distribution and of its underlying population. The mathematical expectation or expected value is a fundamental idea in the study of probability distributions. For many years, the concept has been put to considerable practical use by the insurance industry. And in the last 20 years, it has been widely used by many others who must make decisions under conditions of uncertainty. To obtain the expected value of a discrete random variable, we multiply each value that the random variable can assume by the probability of occurrence of that value and then sum these products. Since the concept of a random variable is fundamental to the idea of a probability distribution, we therefore first discuss it before proceeding to the probability distributions, the characteristics of the probability distributions and their computations. Meaning of a random variable. A random variable is a variable that takes on different values as a result of the outcomes of a random experiment. If an experiment is repeated a number of times with a certain regularity of pattern in outcome, it is called random experiment. In application of probability to practical situations, interest usually centers not on the detailed outcomes of a random experiment, but rather on some numerical characteristics associated with these outcomes. When the experiment has quantifiable outcomes, we define these quantitative outcomes as the random variable. For example, lifetime of a light bulb, or suppose an experiment is to measure the arrival of delivery trucks per hour at a loading dock. The possible outcomes are 0 truck, 1 truck, and so on till we have n trucks. The numbers 0, 1, 2 to n are the values of a random variable, that is, arrival of delivery trucks. When outcomes are not quantifiable, we define a random variable that associates each outcome with a unique real number. For example, suppose a battery manufacturer randomly selects 3 batteries, large batch of batteries, to be tested for quality, which is defective or not defective. We may state it to be a random variable with values 0 if defective and 1 if not defective. Thus, a variable where value is determined by the outcome of a random experiment is called random variable. A variable whose value is defined by a mathematical rule or function for every possible outcome of a random experiment is called a random variable, as defined by Cormel and Paulis. Random variable is also known as a chance variable or stochastic variable. There are 2 types of random variables: discrete random variables and continuous random variables. Discrete random variable is when a random variable can vary only by finite jumps. It is referred to as a discrete random variable. A discrete random variable may take a finite or countably infinite number of possible values. The values of discrete random variables are often whole numbers, usually generated from experiments in which things are counted, not measured. Some examples of a discrete random variable are the total number of heads obtained in tossing a coin 3 times, the number of cars arriving per hour at a toll booth, the number of customers who visit a bank during any given hour. We also have a continuous random variable. So a random variable is a continuous random variable when it can take an infinite or an unlimited set of values contained in one or more intervals. A continuous random variable results primarily from measurement and can take any value ending on the measuring device we use. For example, suppose the maximum average life of a light bulb is 80 hours. Let X denote the life of a randomly selected light bulb out of a lot of 500 bulbs sold by a manufacturer. Then X can assume any value in the interval 0 to 80. Consequently, X is a continuous random variable. Some other examples of a continuous random variable are the price of a car, the time taken by an employee to commute from home to workplace, incomes of employees of an organization. We calculate the probability of the value of the random variable to occur within a certain range or an interval. However, the exact probability of a particular value in a continuous distribution is 0. Technique of assigning probability to a random variable. Suppose that a fair coin is tossed 3 times and we are interested in the random variable number of heads. The sample space of this experiment, that is the number of heads corresponding to each point, and the associated probabilities are shown in our table 4.1. Table 4.1, random variable for a coin experiment. As can be seen, to each sample point there corresponds one and only one value of the random variable, number of heads. A mathematical relationship which has this property is called a function. Hence, a random variable may be said to be a function which associates a real number with each and every sample point in the sample space S. It is customary to indicate random variables by capital letters such as X, Y, etc. It is of course possible to have more than one random variable defined on the sample space of a given experiment. Thus, in our case, another random variable may be the number of tails occurring in the three tosses of the coin. Meaning of a probability distribution. A mathematical relation which assigns a real number to each value xi that can be assumed by a random variable x is called the probability function or the probability distribution of the random variable x. If x represents the random variable number of heads in three tosses of a coin, it can be readily seen from table 4.1 that in an actual experiment, x can assume one of the four possible values, that is 0, 1, 2, or 3. Thus, if we let the symbol x represent one of the possible values of x, then the event x heads occur may be written as capital X equal to small x. For instance, if a trial of the experiment results in the outcome TTT, we say that x has assumed the value of 0 and we may write the probability of this event as probability in bracket TTT bracket closed is equal to probability x equal to 0 is equal to 1 by 8. Similarly, for the event of exactly one head occurring on the three tosses, we have probability HTT or THT or TTH, which is equal to probability that x is equal to 1. And this is equal to 3 by 8 because each one of them, probability HTT or THT or TTH, has probability 1 by 8. Adding them together, it comes out to be 3 by 8. Often, for convenience, we write this more simply as P1 equal to 3 by 8. In general, we shall write the probability that x assumes a value x as Px. An alternative way of starting this is to use the general function notation and write P probability x equal to small x equal to Fx. A mathematical relation which assigns a real number to each value xi that can be assumed by a random variable x such that probability xi is greater than or equal to 0 but is less than or equal to 1. And the sum of these probability xi is equal to 1. Then this is called the probability function or the probability distribution of the random variable x. The real numbers assigned as probabilities to the possible values of x must lie in the interval 0 to 1 inclusive, and the sum of the probabilities thus assigned must equal unity. A probability distribution may be represented in tabular form as a graph or in the form of a mathematical equation. In our example, we have seen that each value of the random variable x has a definite probability. X equal to 0, probability is 1 by 8. X equal to 1, probability is 3 by 8. X equal to 2, probability is 3 by 8 and x equal to 3, probability is again 1 by 8. All these n plus 1 values of the random variable along with the corresponding probabilities are presented in a tabular form, table 4.2. Case study 1. Find probability of boys and girls in families with 3 children, assuming equal probabilities for boys and girls. Solution. If we call x the random variable showing the number of boys in families with 3 children, the probability distribution is as shown in table 3. Table 3, we have number of boys denoted as x from 0, 1, 2, 3. The corresponding probability Px is equal to 1 by 8, 3 by 8, 3 by 8 and 1 by 8. As per table 3, B is equal to event of boy in a family and G is given as event girl in the family. Now, according to the assumption of equal probabilities, probability of B is equal to probability of Z is equal to 1 by half. Therefore, the first answer is that probability of x equal to 0, which means that probability of no boy is probability we have a girl, a girl, a girl. So P, G, G, G is equal to 1 by 2 into 1 by 2 into 1 by 2 and therefore is equal to 1 by 8. Similarly, probability x equal to 1 is equal to probability of B, G, G plus G, B, G plus Z, Z, B. And this is equal to half into half into half plus half into half into half plus half into half into half is equal to 3 by 8. Similarly, probability x equal to 2 by symmetry with the probability is 3 by 8. We can also see that probability x equal to 3 is equal to probability b into b into b. This is equal to half into half into half is equal to 1 by 8. The mean of a random variable. Expected value is an important measure in a statistical analysis. It represents the arithmetic mean of a theoretical probability distribution and of its underlying population. In practice, the population mean is also denoted by Greek symbol mu, read mu. In statistics, the term population always refers to the universe or totality of observations of a variable. The word sample then refers to any group of observations drawn from this universe. We have already dealt with the question of how a sample of data may be arranged into a frequency distribution and summarized by measures such as arithmetic mean and standard deviation or variance. The corresponding population measures are the mean or expected value of a random variable and its variance. So if capital X is a discrete random variable with n possible values xi's, small xi, and with a probability distribution, probability of xi, the expected value of capital X or x written as Ex is defined as Ex equal to small x1 into px1 plus x2 into px2 so on till xn into pxn, or mu is equal to expected value of x is equal to sigma xi pxi and I ranges from 1 to n. In case of a continuous random variable with probability density function Px, the above formulae hold with the only difference that summation is replaced by integration over the values of the variable. That is, expected value of x is now defined as integration from minus infinity to infinity x fx dx. Thus, expected value or mathematical expectation is seen to be a weighted mean of the possible values of a random variable with probabilities as weights. In general, mathematical expectation can be interpreted as the average value obtained in a long sequence of events. Summing up our discussion of expectation in our box, if x is a discrete random variable, the expected value of x is mu is equal to expected value of x is equal to sigma xi into pxi, where I ranges from 1 to n. This is equal to x1 into px1 plus x2 into px2, so on till xn into pxn. Similarly, if x is a continuous random variable, the expected value of x is mu is equal to expected value of x and is now equal to integration from minus infinity to infinity x fx dx, where ex is expected value of x is an outcome value of a random variable, and px is probability of that outcome. The properties of expected value. The expected value of a constant is the constant itself. That is, expected value of k is equal to k, where k is a constant. The second property is the expected value of the product of a constant k and a random variable x is equal to constant k times the expected value of the random variable. That is, expected value of kx is equal to k into expected value of x. The third property is the expected value of a linear function of a random variable is same as the linear function of its expectation. That is, expected value of a plus bx is equal to a plus b expected value of x. The expected value of the product of two independent random variables is equal to the product of their individual expected values. That is, expected value into xy or expected value of xy is equal to expected value of x into expected value of y. Similarly, the expected value of the sum of two independent random variables is equal to the sum of their individual expected values. That is, expected value of x plus y is equal to expected value of x plus expected value of y. In general, expected value of x plus y plus so on will be equal to expected value of x plus expected value of y plus so on. If k is a constant, then expected value of k plus x is equal to k plus expected value of x. Variance and standard deviation of a random variable. The variance of a probability distribution and of its associated population is derived analogously with the variance computed from a sample distribution by weighing the squared deviations of the values of the random variable from its mean by their respective probabilities. The variance so derived, however, differs from the sample variance in that it is a measure of dispersion of the values that a random variable can take over a long sequence of experiments. For example, again, tosses of 3 coins. Accordingly, if x is a random variable with a probability distribution pxi and expected value ex, its variance is defined as, so if x is a discrete random variable, then variance of x, which is denoted as sigma x square, is equal to sigma xi minus mu square into pxi. That is expected value of x minus expected value of ex whole square. For a continuous random variable, variance of x is integration minus infinity to infinity. Integration is from minus infinity to infinity, bracket xi minus mu, bracket close, whole square into pxi. So variance of a random variable, variance x is equal to expected value of x minus ex whole square in both discrete and continuous case, where small x is an outcome which is equal to the value of a random variable, px is the probability of that outcome, and mu is the mean. Computational formula for variance of x. In case of discrete variable, variance of x is equal to sigma x square into px minus sigma x into px whole square. For a continuous variable, variance of x is defined as integration from minus infinity to infinity, x square into fx minus integration from minus infinity to infinity, x into fx whole square. Standard deviation of a random variable, whether it is discrete or continuous, could be obtained as the under root of sigma square x, which is under root of variance. The properties of the variance. The variance of the sum or difference of two random variables is equal to, if the variables are independent variables, then the sum or difference equals the sum of their individual variances. That is, variance of x plus minus y is equal to variance of x plus variance of y. B. If the variables are not independent random variables, then the sum or difference, denoted as variance of x plus minus y, is equal to sigma square x plus sigma square y plus minus 2 sigma xy, where sigma xy is the covariance, a measure of the strength of the relationship between two discrete random variables x and y. And this sigma xy is equal to sigma xi minus expected value of x into yi minus expected value of y into probability xi yi. So p xi yi is nothing but the probability of occurrence of the ith outcome of xi and the ith outcome of y. Variance of k plus minus x is equal to variance of x, where k is a constant. Similarly, the variance of the product of a constant and a random variable x is equal to the constant squared times the variance of the random variable x. That is, variance of ky is equal to k square into variance of y. Case study. In a given business venture, the following information about sales is given by a sales manager. Calculate expected value and variance for random variable sales. We have the monthly sales in units 50, 100, 150, 200, 250, 300. Their corresponding probabilities are 0.10, 0.30, 0.30, 0.15, 0.10, 0.05. Solution. Monthly sales probability, then we have xi or probability xi, we have xi minus expected value of x square, then we have in the next column xi minus mu whole square into probability xi. If you look at all these calculations, we have different columns and we have calculated the sum total in the third column. You can see which is the product of the xi's and their probabilities. So sigma xi into probability xi comes out to be 150. Similarly, in the last column, fifth column, you can see sigma xi minus mu square into probability xi comes out to be equal to 4250.00. Mean of a random variable for sales is equal to expected value of x is equal to sigma xi into probability xi is equal to 150. Variance of a random variable for sales, which is sigma square x, which we have denoted to be equal to sigma xi minus mu square into probability xi is equal to 4250. The standard deviation of a random variable sales in this case is equal to therefore sigma x under root of sigma square x, which is equal to under root of 4250 and is equal to 65.2 approximately.
In this module, we discussed the application of the probability theory to real life situations, when the decisions are based on expectations about the value of a variable. The life of a car battery, as we said earlier, it could be sales of a firm, it could be demand of a product like refrigerator, mobile, etc. So in application of probability to practical situations, we have learned that interest usually centers not on the detailed outcomes of a random experiment, but rather on the numerical characteristics associated with these outcomes. The characteristics we have learned are measured with the help of one or more variables. The variations in the values of a variable usually show systematic patterns in the variation. These patterns are called distributions, indicating distribution of values of variable. Now this module therefore has extended the concept of probability to explain the probability distributions. Or layman's terms, a probability distribution is a numerical or a graphical depiction of frequency counts or probabilities for various values of a variable that can occur. Hence, we have said that a probability distribution provides a complete description of a random variable or the population over which the random variable is defined. However, it is often necessary to characterize the distribution by a few summary measures. The various characteristics of the expected or theoretical probability distribution of a discrete random variable x, the mean denoted as Ex, the variance and the standard deviation. We have discussed that the computations of expected value, variance and standard deviation of the random variable can help select the best decision among a number of alternatives.